right, guys. So this class is for grain boundary strengthening. So defects. How can we categorize defects? Any idea, Roa? Do you know what are the categories of defects?
As in like Frankel and Shockley, these defects?
Like the point defects,
Oh yeah.
maybe one
Vacancy.
type point defect. Can you give one example to point defect? Like vacancies, right? Or substitutional atom, right? Substitutional atom or interstitial atom. What else? Resul?
Line defects hocam.
Line defects, perfect. Line defects. What is the example for line defects?
Dislocations.
Dislocations. And we can divide dislocations into edge dislocation and screw dislocation, right? Dislocations. Third one is interfacial defects. What is the example for interfacial defects?
Hocam, is it the same with planar defects?
No, it's different.
Okay. Sorry.
I thought you said line defects. Yeah, the interfacial defects are planar defects. You're right.
Yes, then grain boundaries and twin boundaries hocam.
Very good. Grain boundary or twin boundary or maybe stacking folds, right? These are all interfacial defects. How about the fourth category? Maybe we might have some bulk defects, right? Or the big volume defects. And the question is, how do they affect the strengthening? So we know how interstitial, substitutional, precipitate, they affect the strength of a material, right? We have solute solution hardening, and we basically have one dislocation stress field. If it is edge, it will create tensile compressive. If it's screw, it will create some shear field. Then the stress field of defects interact with the stress field of dislocation, and they will create some additional hardening, and solute solution strengthening is inversely linearly proportional with the square root of C. And for precipitation, we have like top formula, right? We have critical amount of concentration, precipitation concentration, which changes the precipitation type from cohesive to non-cohesive. That means we cannot shear it. And we will see precipitation hardening. And this course this is for strain hardening. We will also discuss about it. Strain hardening. And in this course, we will check the grain boundary strengthening. The main idea of all of these strengthening mechanisms are same. If anything blocks or hinders the movement of dislocation, create additional strengthening. And for grain boundaries, the main strategy is basically based on reducing the mean free path of the dislocation. That is the main idea, reducing mean free path of dislocation. That means like ending the crystal. Ending the crystal. So it is one of the oldest strengthening methodology, including with solute solution strengthening. So it is very old method. Can you guys give me an example for grain boundary strengthening?
Quenching hocam.
Quenching is like a heat treatment, right?
Yes. So,
Like think about the manufacturing operations.
Hocam rolling process maybe.
Rolling may decrease the mean free path. You're right. Maybe we can have additional hardening. Think about the old swords masters.
Forging.
They
Forging.
basically had one hammer, right? With hammer, they forged the metal. They basically have one swords and they put the hammer and forged the specimen. And they locate more atoms to the specific location. And they basically reduce the grain size and put more atom. And they basically reduce the mean free path of dislocations. The crystalline solids, like the most materials, they generally consist of millions of individual grains separated by boundaries. If you go ahead and check this material, we will have like lots of grains, bunch of grains. These are all grain boundaries. And each grain or like a subgrain is a single crystal. So this is single crystal. And within each individual grain, there is a systematic packing of atoms, right? We have unit cells. This could be FCC, BCC, HCP. And with the repetition of unit cell, we have systematic packing of atoms. Therefore, each grain have different orientation. So this unit cell will repeat itself, whereas same crystal structure, but the orientation of unit cell is this way, this is this way. So atoms are oriented in different ways in 3D. And they have different orientation and they are separated from the neighboring grain by grain boundary. This is the grain boundary. These are all grain boundaries which separated different orientation of atoms. And when the misorientation between two grain is small, the grain boundary can be described by a relatively simple configuration of dislocations, like edge dislocation wall. And we call it low angle grain boundary. If this is oriented in this way, and this one is oriented this way, if the angle between them is less than, some would call it 10, some would call it 15, some would call it 20 degrees, we call it low angle grain boundary. And it is easier to jump from low angle grain boundaries for dislocation. But if the angle is greater than 20 degrees, that means it is harder for dislocations to jump. And grain is just like a sub-volume that has the same crystal orientation and the same crystal structure. So within each grain, we have same orientation and the same structure. Any questions so far, guys?
All clear hocam.
Right. So if we have let me draw it in 2D. Just draw some honeycomb. Think about it in 2D, but of course, the unit cell will be in 3D, right? We might have this kind of orientation, and the unit cell will be something like this. We might have different orientation, and the unit cell could be this way around. So each grain, they have same orientation, same crystal structure. Perfect. So we said we have low angle grain boundaries and high angle grain boundaries. When the misorientation is large, like the high angle grain boundaries, more complicated structures are involved, like a soup bubble simulating the atomic planes in the crystal lattice. The grain boundaries are therefore like the places where the grains meet in the solid, right? So this is the grain boundary, and these two grain meet at this junction. And there are transition regions between the neighboring crystal, because these two are different crystals. They are each single crystal. And there is a disturbance in the atomic packing. So the packing of this crystal is different from this crystal. And these transition regions, like the grain boundaries, these can be also walls, may consist of various kinds of dislocation arrangements. So let me draw another figure. Of course, we are talking of atoms. Let's say we have an atoms oriented in this way. And another packing is this way. We will only see this arrangement in 2D. So on and so forth. Let me define another plane and define another orientation of atoms. It will go like this. And here, let's put something like this. All right. Atomic arrangement is same in each grain. And how do you think we can calculate the angle of misalignment? Basically, let me use different color here. So this is the first orientation, right? And the second orientation, let's do it with this way. This and this angle is misorientation angle. Can anyone help me to calculate the misorientation angle between this grain and this grain? Any idea? So it is the same methodology, right? We will have this alignment and this packing, and the angle between them is the misorientation angle. So let's say this is greater than 20 degrees and it is high angle grain boundary. And here we have low angle grain boundary. And at the grain boundary, along the grain boundary, there is a disturbance in the atomic packing. So if suppose this grain is also oriented this way, like the same with this crystal, then we don't have any disturbance in the atomic packing. So we wouldn't have any hardening due to the disturbance. Since we have this disturbance, if you just zoom in this region, you will see that the atoms are this way and other atoms. Let me draw it in different color. Another group of atoms this way. We have some disturbance in the atomic packing in between. So cracks might start from these regions. They might elongate along the grain boundary, or they just pass the grain boundary. So these are another type of imperfection. Which type of grain boundary do you think will generate more hardening?
High angle hocam. Is it?
High angle, right? And the explanation is it is harder for dislocation to jump from this grain boundary to this grain boundary. Since we have high angle, it requires more energy to jump from first grain to the second grain. And the thing is, we know the average size of each grain, and the grain structure is usually specified by giving the average diameter. And the grain size can be measured by two methods. One is linear intercept technique. This technique is extremely easy, very easy, and maybe preferred method for measuring the grain size. The second method is ASTM procedure. This method of measuring grain size is common in engineering applications, all right? So maybe in the midterm, in the exam, you will see such a, from EBSD analysis, electron backspectral diffractometer, you can observe the grain boundaries. You will observe the grain boundaries, or even with optical microscopy, you can observe the grain boundaries and you will have such a figures. And the question is, what is the average size of grain boundary? And of course, we will have some micron bar. Let's say this is 100 micrometer. And the question is, what is the average grain size? How can we solve this problem? Any idea?
Like, can we count the number of grains in the picture and like divide somehow? It's going to give the average grain size.
Russell, is it you?
Yes, hocam. Like, I would count the number of grains and like use the units 100 nanometer, for example, to
Right.
do some stuff.
Very good, very good. Perfect. Basically, what you can do is you can just draw the diagonal, maybe from both way. You just need to draw the diagonal and draw the image boundaries and count the intercepts. How many intercepts you gonna count? So 1, 2, how many grains you gonna count? And the linear intercept technique, we have a formula. The mean linear intercept can be calculated through L, which is the length of the line, this length. NL, number of grain boundary intercepts. And M. M is just the magnification in the micrograph of the material. So this is just magnification. Then from this formula, we can derive the mean linear intercept. So if you see any micrograph showing the either EBSD, could be optical microscopy, you can calculate the average diameter of the grain boundary. Suppose here length of the line is, let's say, this is, for example, 100 times 10 to the 3 micrometer. This is 100 micrometer, and we have 100 times 10 to the 3 micrometer. I'm just giving arbitrary numbers. Maybe NL, we have 1, 2, 3, 4, 5, 6. NL, we only have 6 intercepts, and the magnification is, let's say, the magnification actually is given in the question. Let's say this is 113. Then you can calculate the average grain size. Maybe it's around 20 micrometer, whatever it is. So the thing is, we have to draw as many lines as possible to reflect the statistical deviation. And we have to draw several lines to obtain statistically significant results. You can either draw these kind of lines. You can either draw these kind of lines, and you can determine the average grain size. All right. So the idea of strengthening was impeding the dislocation motion, right? So grain boundary strengthening, assuming we don't have any slip transmission, and grain boundaries also can impede the dislocation motion. Therefore, they also contribute to strengthening. And the magnitude of observed strengthening depends on the structure of grain boundaries. And of course, the degree of misorientation between grains. So it depends on the average grain size and the misorientation angle. In literature, there are several models describe the grain boundary strengthening. Nearly, almost all of them reduce to the form of the original whole patch relationship. So whole, these are two different scientists, patch relation ship. And what is the whole patch relationship? Suppose we have a grain boundary. Let me just draw a grain boundary. Let me draw two different ways of dislocations. Slip is this way. All right. Dislocation slip. And it may, like, depending on the slip plane, it may slip along this way. Can jump to this way. Or maybe we also have different slip system, and they can jump to this way. So the misorientation is this angle. And here we have another misorientation angle. And the slip transmission from here to here depends on the angle. If it is a low angle grain boundary, it is easier to jump to another grain. If the angle is high, the dislocation may not move, or it's extremely hard. You need to require a lot of energy to jump from one grain to another grain. Therefore, dislocation can be stopped at these grain boundaries, and there will be pile up. Another dislocation will come here and annihilate the first dislocation. This will come here, this will come here, and we will see a pile up of dislocation. Let's assume we have a grain size of D. This is the average grain size. The shear strain due to the average grain size can be calculated through Berger's vector dislocation density times the average grain size. Therefore, the dislocation density total of mobile and immobile dislocation can be calculated through gamma divided by B times D. And we have a classic formula. Shear stress is nothing but a constant alpha in between 0.3 to 0.5 times the shear modulus times the Berger's vector times the total dislocation density. And sigma is equal to Schmidt factor times the shear stress, which is equal to Schmidt factor times alpha, G, B, and rho. I'll just put this equation into rho, and we will come up with sigma is nothing but mu times alpha times G times B shear strain divided by BD. And I will just include them in one constant, which is K, and D to the minus 1 over 2, because D is here. And of course, sigma, we have some prefactors, right? Maybe we begin with some lattice resistance, sigma 0 plus K. This is always defined by polycrystal. And we have D to the minus 1 over 2. And D is the grain size. So what happens according to this formula if we decrease the grain size according to Hall-Page relationship? Are we increasing the strength or decreasing the strength once we have the less grain size? So less grain means more strength or less strength? Rohan? If you decrease this value, are we going to obtain more stress, more strength, or less strength?
If we decrease which value now? D?
D, yeah.
I think we will have less. If we decrease it, we will have more. Sorry.
Right. Once we decrease the denominator, we will increase the total result. So far, so good. Any questions so far?
No,
Any
hocam.
question, guys? How about if we have like dislocation pileups? Suppose we have Frank Reed source. All right, we have a grain boundary. We have a grain, sorry. And we have Frank Reed source. Let me just draw it this way. And we have Frank Reed source. This is Frank Reed source. And we give shear stress to the material. And the additional shear stress is mu B divided by L. And what is L? It is just length of the grain, right? This is the L. This is the distance. Let's say this is D, the grain size, and the minimum torque that activates the dislocation motion, the Frank Reed source, to generate dislocation is, instead of L, we will use D, mu B over D. Once we have this excess stress, we will have dislocation motion. And we will have something like this. It will, let me draw it again. We have the grain size is D. Then we have Frank Reed source. And the dislocation loop occurs once we have tau is equal to mu B times D. Then it will, so we will have something like this. It will expand and pile up to the grain. It will go till grain, assume we don't have any slip transmission, and it hit the grain boundary and there is no slip transmission, okay? So it stops. Then what is the next amount to generate the second dislocation? How can this Frank Reed source will generate dislocation? What is the excess stress? Do we require more stress or less stress to generate the second dislocation? Resul?
Like, I actually don't know, hocam, but I would say less stress because the more stress is spent on the first one, I guess.
You said less stress. How about the others? Kaan, what do you think?
Hocam, I think it must be more.
And what is the reason? The formula is here. The excess stress will be this. To generate the first dislocation, the length is D. This is the minimum because right now, the next step, we will have a length less than D, right? The length is less than the average grain size. So we will have less value for D. If we decrease this value, that means we need more stress to activate the second dislocation. Once we activate the second dislocation, it will hit and stay at this location. Then we will again need more shear stress to activate the third dislocation because this L, this time, less than the previous L. Let's call it L1. Right? Then, until we have lots of dislocation motion, every time we are increasing the excess stress. that means we are generating more strength. So the pileup has strengthened the material because we are decreasing the mean free path of dislocation. Is it correct? So we can conclude that the pileup due to grain boundary has strength and the material. Perfect, perfect. All right. So delta tau is basically alpha mu b d plus the additional stress of pile up. And it is related to 1 over d. So Hall pitch relationship. Pile up, let's put it this way. Think about we have in opposite sign of Burgers vector. The separation distance is always decreasing, don't forget, since we have pile up here. And the opposite sign, so shear stress is this way, shear stress is this way. Opposite sign of dislocation. Here, the length is this. When dislocations generated by source, Frank Reed source, approach obstacles on slip plane, they often pile up. And the obstacles include grain boundaries, any second phases, like in superalloys, we have gamma and gamma prime phase, and phase boundaries, any sessile dislocation, and it leads dislocation is acted on by applied shear stress and interaction forces like the back stress from another dislocation. So they repel each other. And number of dislocation in the pileup can be calculated as K. So this K is 1 for screw dislocation, and for H dislocation, it is 1 minus Poisson's ratio for H dislocation times pi times shear stress times L, or the maximum is D, right? The maximum N divided by G times B is the number of dislocation in pileup. And of course, once we have pileup, we will have some stress concentration. Consider at a grain that consists of a single dislocation source like this S. This is the source in the center. Dislocations emitted from the source can go this way or this way within the individual grains. And this is Frank Reed source, which generates the dislocation. And they encounter a lattice friction stress. They need to overcome the peerless stress. This is tau zero. This is the lattice resistance in order to move these dislocations. So this is, let me call peerless stress. For FCC material, the lattice resistance is very low, maybe 5 megapascal, even 1 megapascal, depending on the temperature, of course. But for screw dislocation, it is very high. The lattice resistance is high. And the lattice friction stress opposes the applied shear stress. This will reduce. So the net shear stress is the applied shear stress minus the lattice resistance. Let me call it tau zero. And this is, let me call it not net, but the effective. This is the effective stress that contributes to plastic deformation. The stress to make a dislocation to move is the applied stress minus the lattice resistance. And since dislocation motion is impeded by grain boundaries, dislocation will pile up at the grain boundaries, and they will pile up until the stress is large enough for them to break the grain boundaries and pass to another grain boundary. And in this model, think about the effective stress. Grain boundary strengthening is effective stress, which can be calculated through applied stress minus the lattice resistance, D minus D divided by 4R. And D is just the grain size, and R is the distance from the source. And the quantity can be calculated through this term. This represents stress concentration on lead dislocation. Any questions so far?
Yes, William, I couldn't understand the part of the source, FR source. What is that?
The Frank Reed source is the source that generates the dislocation. This could be one extra plane, like this is the imperfection, dislocation source. This will create dislocation. If our source, we generally represent them by pinning 2 points, and all right. Let me call it this way. Once you apply a shear stress, there will be, so this is the source. This is the main imperfection location. Once we apply stress, it will generate dislocations, and the dislocation will move, slip along this atom. So we have unslipped region. The dislocation will come here, it will come here, and it will go till the end of grain boundary. So Frank Reed source is the original source of the dislocation, and we generally represent them by discrete lines. It will elongate, elongate, elongate. Then it will lead for its movement. And we need some shear stress to activate dislocation movement. Is it fine, Roa?
Yes, it's clear now.
Any other questions? All right, so grain boundary strengthening. Think about, let's focus on, let's assume that bulk yielding, so tau applied, is equal to the yield stress, occurs at the critical value of grain boundary, okay, tau grain boundary. we can rearrange the equation as T applied is equal to tau 0 plus tau grain boundary for R divided by D. And basically, grain boundary and R, they are essentially constants, and which can reduce the equation into tau yield stress is equal to tau 0 plus yield prime d to the minus 1/2. So this is the whole pitch relationship, right? Derived from yield stress is equal to sigma 0 plus yield d to the minus 1/2. Of course, there are other models for grain boundary strengthening, but the most widely used one is Hall patch relation. The other methods, I'll just write it for you. There is a AH Cottrell method. I think there is a journal called, the title is Theory of Brittle Fracture in Steel and Similar Metals. That is just a modified hole pitch model. So it's virtually impossible for dislocation to burst through grain boundaries. And it assumed that the stress concentration that produced a pileup in one grain activated a dislocation source in a neighborhood adjacent grain, and the maximum shear stress at the distance ahead of the boundary is given by tau is equal to applied minus tau 0 d over 4r, where tau is the stress required to activate the source. This is the stress required to activate the source in the adjacent grain. And we have applied shear stress at which the source becomes active, and tau 0 is just the parallel stress again. And yeah, this is another model, but this is just the modification of whole pitch relationship. We have another model. I forgot the name. Forgot the name, but this is again same with whole pitch relationship, right? Whole pitch relationship. I think there was one Chinese guy, I think Lee method. It is again like the pitch relation. And in this model, the ability of grain boundary to emit dislocation can be characterized by new parameter mu, and the new parameter is just total length of dislocation line emitted, the total length, divided by the unit area of grain boundary. And the parameter mu also related to dislocation density at yielding, via dislocation density is 3 times mu over d, and the rest is same with Taylor model. So it's equal to tau 0 plus like the same Taylor model. You just put this equation into this, and it is, once you combine this term, you will also see that it is more or less similar to the whole pitch relationship. All right. How about for nanocrystalline materials? Nanocrystalline means these materials with the grain size less than 100 nanometer. Is it like very strong materials? they can be viewed as composites consisting of small dislocation-free crystals in amorphous matrix, and the grain boundaries are on the order of 5 nanometer in width. So do you think nanocrystalline materials are very strong? Yeah, basically they are strong. Once we decrease the, let me just draw stress versus d to the minus 1/2. We will see for different materials, different responses, but stress is always linearly proportional with 1/square root of d. Perfect. And don't forget, once we have, like during loading, stress strain, think about like we have stress versus strain. Here we have less dislocation density, and once we elongate the material, we will have more dislocation densities, and the dislocation density increases as the plastic strain increases, and dislocation tangles and cells will increase like the subgrains, and we will increase the strength due to grain boundary strengthening. Perfect. So that is more or less it for grain boundary strengthening. Let me just delete this page and add another page. So far we covered solute solution hardening, and we said that the nature of obstacle is solute atom. So this is the hardening mechanism and nature of obstacles. And type, let's say type. It is solute solution is a weak form. It's not very strong. And delta tau is linearly proportional with square root of C. And this is hardening law. We've covered precipitation hardening, and we can divide precipitation hardening into two. What are the two categories of precipitation hardening? Roa, what was the main categories of precipitation hardening?
I can't remember right now.
With small particles, right? With coherent particles, deforming particles, and with large particles. For small particles, again, it's all precipitation. Type is weak. And it is more or less similar to solute solution hardening. But once we have large particles, again, precipitation, it is strong. And the hardening law is basically delta tau was GB divided by L minus 2R. And today we've covered the grain boundary strengthening. Whole patch, right? Whole patch relation. What is the nature of obstacle, Resul, that stops the moment of dislocation?
Like existence of grain boundaries hocam. Is it
Grain
what?
boundaries, perfect. Grain boundaries. Is it strong or weak?
Like the more grain boundaries we have, the higher strength we have hocam.
Yeah, it is a strong type of dislocation, and tau is just proportional with the inverse of grain size. That is basically it for grain boundary strengthening. Any question? If not, I'll stop at this point. And let me just stop the recording.